If we have too many neutrons, that's no good. If we have too many neutrons, then we need to convert a neutron into a proton by beta emission. If we have too many protons, then we need to get rid of some of those. One way to get rid of too many protons to neutrons, it's a proton to neutron to proton ratio. And so what we can do here is we can get rid of a proton, actually not really get rid of it, but convert a proton into a neutron by positron emission. A positron emission, one way to think about that is just a positive electron, a positron. And so if we have a positron, it's going to be beta, but with a +1 rather than with a -1 here. A positron is what they call antimatter. And so when you combine antimatter with matter, it just forms energy. So if you take a positron and a beta particle, combine those, they'll make energy. Commonly encountered in artificial produced radioactive nuclei of the lighter elements. So here we have P, if you look at P, it only has 15 protons, so you wouldn't expect it to be all that unstable, but what makes it unstable is unfavorable, neutron to proton ratio. It's an unfavorable neutron to proton. That is, if we have 15 protons, we like to have how many neutrons? And you look, there's only one isotope of phosphorus found in nature, and that's what's the one isotope of phosphorus found in nature based on the average atomic mass? 31. So if you have 15 protons, you like to have 16 neutrons holding it together. Well, it turns out 15 neutrons is not good. And so this has an imbalance of neutrons and protons. And one way that this can help is to convert one of the protons into a neutron by positron emission. So here's a positron, which is this. And so we convert it. And so when we lose a positron, then we go to element number 14, which is silicon. This will be silicon 30. It's positron. Here is a cloud chamber decomposition. Let's talk about electron capture. Electron capture is like positron emission in that it converts a proton into a neutron. And so here, if we look, electron capture is actually capturing one of the core electrons. So the nucleus is unstable. It captures one of the core electrons. If it captures one of the core electrons, then 81 gets converted to 80. And then we still have the same mass number. So we just converted a proton into a neutron. And so we end up forming mercury. But here is where nuclear chem might be interested in electrons, because if you capture a core electron, then you have a hole in the core shell. That hole needs to be filled. It's quite unstable. And so this is why it's double dagger. And what happens is this electron goes from a valence down to a core and emits an X-ray in the process. And so emits a photon of light.
I think there's a typo. It's supposed to be TL instead of TI.
81. We can figure that out. Yeah, you're absolutely right. 81 should be TL, which is thallium. TL is thallium.
What's the difference? So the beta part of here is the electron is negative. What was the one in the previous slide that's positive?
It's a positron.
Yeah.
Positron, which is a positive electron. This is a positron. So beta is electron. Positron is a positive electron. Electron capture is just capturing, sometimes they'll write E rather than beta. It's not really a beta because a beta is actually originating from the nucleus, right? And so this is just an electron coming from the core. Electron.
It's being consumed or emitted?
Consumed.
Okay,
Yeah. And so this is the nucleus. There's a core electron. It gets sucked into the nucleus, let's say, converts. The electron gets sucked in the nucleus is going to convert a proton into, because an electron is a Yeah.
Sorry, where did the electron go from?
The core.
So just emitted it and then.
Yeah, so let's say this is the nucleus here, this core electron here. One of the electrons in the core gets absorbed in the nucleus. Okay, if electron gets, from the core gets absorbed in the nucleus, then that leaves a hole here. That hole has to be filled by a higher energy electron dropping down. Higher energy would be maybe a valence electron up here, drops back down to the core and emits a photon. This would be an excited state.
So you decided that it was going to be.
Well, it's very unstable, so it's going to try to minimize the energy. So this is one way it can do it. It's not,
So is the positron not part of the core shell? Is it just
No.
in the?
A positron is like this. If you have a neutron in the nucleus, the neutron is 0, 1, and a neutron emits a positron. Well, actually, it doesn't emit a positron, doesn't it? A neutron emits no, not a neutron. We can't have a neutron because a positron is plus 1, 0, right? And so this has got to be a proton. A proton is a 1, 1. So the Z is 1, mass number is 1. Now it makes sense because now this plus 1 can combine with a 0 here and a 1. So a positron emission is when a proton gets converted into a neutron and spits out electrons. But the proton itself didn't have any electrons to begin with. It was just a nuclear reaction process.
So when you say it spits out an electron, but
It spits out no, not it spits out an electron. It spits out a positive electron, a positron. It spits out a positron.
How can electrons be positively charged?
Nuclear. Yeah, ask one of the particle physicists. Actually, there are a lot of talks from particle physicists. I think this is one of the most popular topics of physics talks. There's a whole bunch of things on that. Well, this is why, getting back to Scott's question, if we could shield ourselves from the alpha particle, fine. But unfortunately, thorium is radioactive too. And in the next step, thorium comes out as an excited. Whenever you see this double dagger, it just means it's excited. It's an excited state. And it can't stay there forever. It's going to drop down to its ground state. Even though this is still unstable, it can drop further down. But in the process of going from this excited state down to this ground state, it's going to emit a gamma ray. And the gamma ray is the problem, because gamma rays are highly energetic, and so this is what we call ionizing radiation. In fact, all these are ionizing radiation. Ionizing radiation can either take electrons or knock electrons off or break bonds. That's ionizing radiation. And so gamma rays are highly ionizing. These can easily break bonds. They have enough energy to knock electrons out of bonds, cause a lot of damage, or make free radicals, make ions, make whatever else you can do by knocking electrons off. Right? And so gamma radiation is bad because gamma rays are highly penetrating and energetic photons. So what you need to do, X-rays, you have lead. You go to the dentist's office or whatever, they put a lead apron over you, But if they're going to hit you with gamma rays, you don't use a lead apron, you use lead brick. And you can calculate the thickness of lead brick that you have to use based on the energy of the gamma ray that's emitted. And we're going to have different energies of gamma rays, some higher, some lower. But you're going to need a lot of shielding to protect you from gamma radiation. So a lot of nuclei that are found in nature are just naturally radioactive isotopes, like uranium. Uranium's mined as uranium ore. In fact, we have a piece of uranium ore in the back here.
Uh-oh.
I'll show you. I don't know if you want to see it. Do you want to expose yourself to radiation?
Yeah, let me see it.
Yes?
Yeah, it's mostly plutonium. So.
All right, I'll bring it out if they didn't. There was a huge cleanup, and so I'm not sure if it's still there. It wasn't properly shielded.
Does it still glow?
There was lead. It was probably shielded enough because there's lead.
Does it still glow?
No, it doesn't glow.
Okay. We'll take a look.
Yeah, we'll see if I can grab that tomorrow. All right, so uranium decomposes, emits an alpha here. And then thorium continues. And then this. So some palladium, not palladium. Palladium is, yeah, nice. Yeah, maybe this is palladium. Element 91. This is 91. No, it's not. This is something else. Pascalium or something. All right. That'll be. And then, and so there's a bunch of naturally occurring, and a lot of these just come from the decomposition. You don't have to know any of these here.
We don't.
No. What's that? Oh, okay, thank you. Titanium. That's probably named after somebody. Daughter nuclids. Okay, this is what we call the parent, and these are all daughter nuclids because these are all from the same parent. And there's a daughter nuclid. Nuclids just being a specific isotope produced by radioactive decay. Here. This is a decay series. And so the red line is an alpha, the blue line is a beta. And so if you start off with U238, then we'll have an alpha, beta, beta. And this changes. You can see how it changes here because an alpha, you lose 2 protons, so you're at an element 90. A beta converts, beta emission converts a proton into a neutron, is that right? Or a neutron into a proton. Beta. Yeah, the way you can figure it out is you just try it and see. You know, if we tried to convert a proton by using beta, beta is a -1, right? And so what would we form here? Well, if we have beta, we get 0 and 1. So it converts a proton into a neutron. Well, what if we did a neutron? Will a neutron undergo beta emission? And so -1 plus what? Proton. Well, maybe a proton here. Does that work?
That's right. Come out 1 0 if it's
Yeah, how about this one? Is this one right?
one there.
-1 plus 0 doesn't give us +1, so this can't be right. It's got to be converting a neutron into a proton, right? If you convert a neutron into a proton, it's going to jump up 1 in Z, right? And so you can see beta, beta, alpha, 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 and then we have a branch here. This can either go alpha or beta. It will form different daughter products. Eventually, you know where we end up? Element 82. Element 82 is lead, and then it's no longer radioactive. Lead is stable. This isotope of lead is stable. We could have other isotopes of lead which are unstable. But eventually we end up at lead, and then the series, the decay series is done. Well, how long does this take?
I thought about the two positrons, are they emitted naturally, further on than not, because wouldn't it be highly reactive with?
Oh yeah, it would be.
It doesn't necessarily occur naturally right now.
in this outer space.
Well, let's see. You know what it said about positron emission here was that commonly encountered and artificially produced. So artificially produced or man-made radioactive isotopes. Yeah, not likely to occur. And naturally occurring isotopes. Well, all these here would be naturally occurring isotopes. In fact, radon here is a big concern. A lot of granitic soils contain uranium, because uranium actually gets trapped in, I think, garnet crystals, as a hole in the garnet crystal that is really good for trapping uranium. And as that starts to decompose, eventually it hits element number 86, radon. Well, radon's a gas, can escape out of the solid.
Crystal phase.
Yeah, out of the solid. And you end up inhaling it. And radon undergoes boom, alpha, followed by beta, etc. How long does this process take? Well, all these are dictated by first order kinetics. And so, the first step is first order kinetics. The first step has a half-life of something huge, And so the case series, this takes a long time, basically. Okay, let's talk about this. These are just what we call natural decay processes. Natural decay processes are like you have a big nucleus or you have a bad neutron to proton ratio. A big nucleus, you want to get rid of some of that. A bad neutron to proton ratio, then you'll want to use some of these beta positron, electron capture. But there's something called nuclear synthesis. Nuclear synthesis, this is how the elements, the world, they thought if there's a supernova explosion, this is how you can make bigger atoms from smaller atoms by fusing them together. And so this is an example of nuclear synthesis here. So if we take a nitrogen-14 and a helium and combine them, we can form these, oxygen-17 and hydrogen. But the nuclear synthesis, there's problems with nuclear synthesis. One of the problems with nuclear synthesis is that the two nuclei repel each other strongly. And so how do you get the two nuclei to collide with each other? Well, you need extremely high kinetic energies to do that. And so typically, when you're looking at synthesizing, doing this nuclear synthesis, we usually use something like this, a linear accelerator, or cyclotron, which is a circular accelerator. And so one way you can overcome the repulsions between the two nuclei is accelerate them to very high velocities so that there's going to be a gigantic collision. A collision can get those nuclei to react with each other. Right? And so nuclear synthesis is going to rely on accelerating particles. The way they accelerate, you can accelerate particles by using you use electric and magnetic fields. You use electric and magnetic fields to contain the particles in space and then accelerate them along a path. And so here you can do some synthesis. For example, here you can make like even new atoms, like californium plus nitrogen. So uranium. This can't be uranium. What's element number 105? DB.
DB, whatever that is.
Yeah. I know it's as a G, Seaboard. Seaboard, he's a UC Berkeley professor. He went to UCLA too.
We had
He's
to
a
copy
very
this
famous
down.
UCLA alumni. No, but this is wrong. This cannot be uranium. These are the transuranium. The transuranium elements are all man-made. These are like taking nuclei and then smashing them together, atom smashers. And Berkeley is a hotbed of this activity because they have a very powerful accelerator there. And so all these are man-made here.
Does this have really short half-lives or long half-lives?
This, actually, the man-made list goes all the way out here.
Didn't do one.
Yeah, all the way up there. But you don't have to know any of these. You don't have to write this down. Okay, so what types of reactions do we have? We have reaction to break the nucleus into smaller pieces, smaller nuclei, alpha. We have reactions to convert protons into neutrons and neutrons into protons. We have nuclear synthesis, in which we could use an accelerator to make new atoms, like in a supernova explosion. Supernova explosion is what, they're taking hydrogen, helium, and making other atoms like oxygen, etc. But they can do it in the lab too, using accelerators. Right? All right, as far as we're just going to go in the order of this, but as far as the kinetics of this goes, let's look at the decay processes. Decay processes would be alpha and beta primarily. Alpha and beta are the two most, important ones. If you look at that uranium decay chart, then you'll really want to know alpha and beta emission, right? And then gamma is a product of that, because gamma is, when you get the excited states dropping down to the ground states. But if you look at this, what do we call this? Well, we call this the integrated rate law for first order kinetics, except rather than ln of concentration at time t over the concentration at time 0 times kt, negative kt, we use this. It's a number, at time t over the number at time 0. This would be the, radioactive Euclids. And lambda would be the rate constant here times t. And so this first order kinetics. This is just going to be proportional to the number of atoms there. Well, first order kinetics will have a constant half-life, and so it's much easier to talk in terms of half-life than in terms of rate constant, which would be 0.693 over the half-life. But here, the half-life, there's huge variation in the half-life. The smallest one here is 10 to the minus 3, 10 to the minus 4 actually. The smallest one is 10 to the minus 4 polonium. Polonium is very short half-life here, 10 to the minus 4, but not short enough for the journalist who got poisoned from that. And the longest one would be, yeah, 10 to the 9.
1.51 times 2.
Yeah, 10 to the 9, uranium-238, 10 to the 9 years, so that's what, billion years, 4.5 billion years half-life. Yeah, so it's going to take a long time for uranium-238 to decompose.
Is that why Chernobyl's still in a lot of trouble right now because of that reason? The half-life's so long on the radioactivity there.
Oh yeah, Chernobyl still.
They're going through their first billion years.
Yeah, Chernobyl. I guess they're going to have to redo the lid on Chernobyl. But the same thing, and at least they have a lid. I think Fukushima. But it's a different kind. The type of reactor, nuclear reactor, Chernobyl was a graphite reactor. And graphite's fairly unreactive, but Chernobyl incinerated the graphite completely. Anyway, going back to this, iodine is a very important one because a lot of iodine was released at Fukushima. Iodine has a half-life of 8 days. And so there's a rule of thumb. The rule of thumb is it's going to take 5 times the half-life for the activity to drop down to where you consider, 5 times the half-life is about 99.9% reaction. It gives you 0.1% left over. Well, we can calculate it actually, but so 5 times 8 would be
40 days.
40 days, and then the activity of the radioactive iodine goes way down. But they're finding, one of the things is they're finding iodine well after they said the nuclear reaction, and so it was giving evidence that there's still some nuclear reaction occurring because of radioactive iodine is still being produced in that particular reactor. P32 is another one. P32 is very common with biochemists. P32. And so, the biochemists on our research floor had all kinds of little radioactive, low-level radioactive things. It has a half-life of 14.3 days. P32 is good for biochemists because they can track where the phosphorus ends up. So if there's a phosphorus going in, they want to know where it's going to in metabolism.
Actually about how come bromine has a short half-life?
I don't know. I mean, it just, that is what you want to ask a nuclear chemist, a theoretical nuclear chemist, because, these are just our observations, and it's the job of the theoretical chemist to come up with a description of what's going on. And so you have a lot of observations like this, and that's an excellent question. Theoretical chemists will want to know why and how to predict, The theoretical chemist doesn't want to have to measure these. The theoretical chemist never wants to go into the lab. The theoretical chemist is always at the computer and looking in books, right? And so they want to be able to predict these things without having to do any kind of measurements. But, you know, the theory, I don't think it's at that level. I don't think, you know, if you ask a theoretical chemist, and I need to ask a up-to-date theoretical nuclear physicist or nuclear chemist, you know, can you predict the mass for me so we don't have to measure the mass by mass spectrometer? You know, I'd like to ask that, you know, something like that. But I haven't. But, you know, they say, you know, with this Haldren, I've been watching some of this stuff, and they say, oh, I think the state of the art is beyond what's in the book here, because what's in the book are just observations, you know, and patterns. But apparently they have the theory pretty well sorted. At least that's what they say, up to a certain point. And so things like predicting nuclear spin, you know, and other stuff we'll talk about. At UCSB, this is on a different track, but you know, the biochemists were working with this. Whereas over in chemical engineering, there's one guy who was putting, you know, I think yeast cells or something, or some bacteria, I forgot, yeast or bacteria, into into an NMR, nuclear magnetic resonance spectrometer, and then bombarding it with gamma rays. And so, and then tracking the metabolism by measuring, you know, phosphorus. You can measure hydrogen, or you can retune. You know, you can retune your NMR to measure phosphorus. So you retune the NMR to measure phosphorus, then you can track the phosphorus. And so he was tracking the metabolism of yeast, I think, upon bombardment with gamma rays to see, you know, how that would affect humans. What's that? Oh, okay. I'm sorry. I thought you had a question. All right, one of the big applications of kinetics in nuclear chem is radioactive dating. You know, how long? Well, how long it takes, we just need the, what we call the daughter-parent ratio, or, you know, these are isotope ratios. It doesn't have to be daughter. In this case, it's carbon-14, carbon-13 ratio. But we take isotope ratios, and then we can determine the
percentage of
light, right, of these. And so apparently, this radioactive, you know, is induced, and then the decay process starts. So living organisms maintain a carbon-14, carbon-13 ratio at equilibrium. So we can measure this ratio using a mass spectrometer very easily. In fact, you know, this is called isotopic fractionation or isotopic ratios. You know, it's very easy to tell the difference in, for example, oxygen at sea level versus oxygen at higher altitudes by looking at the isotopic ratios. You know, the natural abundances aren't constant. Percent natural abundances fluctuate depending on where you are. And those percent natural abundances are averages. So when you see that hydrogen 1 is 99 point whatever percent abundant, then that's an average. And so one of the applications in isotopic fractionations is looking at ozone. You know, is the ozone from the ozone layer, or is the ozone from pollution? And it's very easy, because ozone in the ozone layer has much higher percentage of oxygen-16, whereas the ozone from cars and electronics and other pollution is going to have much higher 17 and 18 than what's observed at higher altitude. Well, anyway, we can measure these ratios easily, and from those ratios we can figure out the age. The half-life of carbon-14 is like 5,000 years, 5,730 years. And so, you know, this is only good to out to maybe 5 half-lives, something like that, or less, you know, depending on how many sig figs you get out of it. And so you can only go to tens of thousands of years, but if you want to go farther beyond that, you can use something with much longer half-life, like U-238. This is 4.5 billion year half-life to get 14 steps and 4.5 billion year half-life to get to lead-206. You know. This is just summing up all those steps, like Hess's law.
Wow.
Yeah. And so,
Amazing.
then this is a parent, this is a daughter. From the parent-daughter ratio, you can get it. Now the parent-daughter ratio is not going to tell you, because when we look at this, you know, it's the ln of the, you know, it's going to be the ln of lead or ln of uranium. It's going to be the ln of uranium at time t over the uranium at time 0. However, what we get is we get lead to uranium ratio. All those lead atoms came from uranium. And so what we have to do is, in order to get the uranium at time t is easy because that's given in the ratio. But the uranium at time 0 requires an extra calculation. The uranium at time 0 is going to require you to convert all the lead back into uranium, and that's going to be the total uranium at the beginning of it. And so,
Is that a hassle?
no, it's not a hassle, but a lot of people skip it because they just, you know what a lot of people do is they just say, okay, one of these is lead, the other is uranium. That's not correct. This should be uranium at time t plus the lead, right? And so, but some people just put the lead in there or somewhere or mix these up, you know, something like that. We'll look at a sample calculation. And so this is just showing that the uranium at time 0 is going to equal the uranium at time t plus the daughter, which is the lead. So this is uranium plus lead. Right? And then we can plug it into the equation. This we're not going to get into this that heavily. We're just going to do simple. If we do, you'll see a simple kinetics calculation in there. So that's kinetics. The thermodynamics part, the energy part, is given by this, the energetics of nuclear reactions, E equals mc squared. You're going to see that there's going to be a mass defect in chemical, actually there's a mass defect in all reactions, whether they're chemical or nuclear. And so in chemical reactions, delta E is too small to notice, right? Because the mass changes are negligible. The mass changes are actually too hard to measure. Even with a mass spectrometer, you can't measure the mass changes. But in nuclear reactions, the mass changes are measurable using mass spectrometer. Mass spectrometer can go out to 6, 7, 8 sig figs now. You know? Nuclear physicists like to use electron volts, EV. EV stands for electron volt. Electron with a volt potential. And 1 mega electron volt is 10 to the minus 13 joules. That's a mega electron volt. And so if the mass change is 1 U, this is enormous. A 1 U mass change, you know, that's gigantic. Then delta E is 10 to the minus 10 joules. Well, how much coffee can you heat up with 10 to the minus 10 joules? Not much. But the problem is we're talking about different scales because nuclear physicists and nuclear chemists don't talk per mole. They talk per nuclide or per atom, right? And so if this is the amount of energy per atom, then what we have to do is, if we want to put it into terms we understand, we have to convert that into moles per mole by multiplying this by Avogadro's number. If we multiply this by Avogadro's number, it would be times 10 to the 23rd. So times 10 to the minus 10, that's going to be 10 to the positive 13 joules. 10 to the positive 13 joules per mole is huge, right? Because 10 to the 13, well, 10 to the 12 is Well, let's see. It would be 10 to the 9 is billion.
Oh, it's trillion.
Let's see, a trillion. Be over a trillion joules. It's huge. Huge. Or 931 mega electron volts per
Like
nuclid.
it's 10 to the negative 10, right?
Yeah.
But
But
how is that huge?
how is 10 to the negative 10 huge is because nuclear physicists like to do it per nuclid, whereas chemists like to do it per mole. And so if we do ours, you know, a typical thing for us is like the ionization energy of hydrogen. Ionization of energy of hydrogen is like over 2,000 kilojoules per mole, which is like 10 to the minus 19 joules per atom. Right? And so well, 10 to the minus 19 joules, is that all that much energy? No, but it is. It is a big amount of energy because in order to ionize hydrogen, it's big. And so what we have to do is we're talking different terms. So we have to align ourselves with the nuclear, or we convert this into terms we understand. This is joules per nuclid. And so we'll have to multiply this by Avogadro's number to get it into joules per mole, what we understand. We saw this in chapter 2. In chapter 2, we see the mass defect. The reason you have to measure these with a mass spectrometer is because when you add up the individual masses, the sum of the individual masses is always greater than the actual mass of and so we've lost some mass. Well, in this particular chapter, we can figure out how much energy was converted into mass. Let's just do this because it's a very simple calculation. This is probably some of the easiest, at least, you know, these simple calculations like this are pretty easy. And so how much mass did we lose? So delta M is equal to mass final minus mass initial. So the final mass is 4.0015 U minus the initial mass 4.0320 U. And so the mass defect here is going to be we lost minus 0.0295 U. Is that correct? So we've lost this much mass. Well, what happens is that much mass is converted into energy. And so this is going to be highly exothermic. And so delta E is equal to delta MC squared. And so we plug in our delta M. Our delta M is minus 0.0295 U.
So I got minus 0.305.
Oh, 305. You're right. It's 305. I miscalculated. 305 U. 305 U. That could have been a huge error. There's different philosophies, you know. Some philosophies say you either get it right or you get it wrong. It's either full credit or zero credit. And their argument for that is, you know, if you get it wrong, it doesn't matter if it's a minor error or a major error. It could result in a dead patient or in a huge loss, financial loss. And so that's why they say. Yeah. And so, yeah, I thought, okay, but you know, this is why we have peer review, and this is why we have people, our peers, checking our answers for us, right? Make sure we didn't make a mistake. But maybe I rely too heavily on peer review. You know, maybe I should be more careful. Because I just saw an article in the LA Times. Did you see it? The number 3 cause of death in America.
That information?
Did you see the number 3 cause of death in America? Mistakes at the hospital. Can you believe that? Then I thought, boy, I need to change my grading philosophy. It's gonna be either all right or all wrong. Otherwise I might not be here after my next hospital visit. It's funny, but it's sad. Yes. They need to do more peer review maybe in the hospital, you know. Let's just ask, or maybe make that, you know, just can you check my answer, because sometimes you get locked into some kind of mistake.
Sometimes, like when you do an operation, if you need an operation on this leg, you do it on the right leg instead of the left leg.
No. Yeah, hopefully they don't make that kind of mistake. Anyway, C is 2.998 times 10 to the 8 meters per second. Now the units are very weird because it's going to be U, M, S, meter squared, second squared. But mass times meter squared per second squared is actually a joule if this were in kilograms. And so what we're going to do is we're going to convert U into kilograms. And so how many U are there in a gram? How many U in a gram? Don't look it up. You should know this. No. You guys know.
Divide by number.
Yeah. So in 1 gram, there are 6.022 times 10 to the 23rd U. Where did this come from? This comes from the definition, the U and the mole. If you add up or multiply those two definitions, you get it because, I don't know if it should review that. There are 12 U in a carbon-12 nuclide. And there are 12 grams, right? Actually, I should do it. In a mole of carbon-12 nuclides, there are 12 grams exactly. These are all by definition, 12 grams. And there are 6.022 times 10 to the 23rd nuclides per mole. And so dimensional analysis, you could figure this out using dimensional analysis. It would be a basic problem. And so then we convert this into kilograms, a kilogram per 1,000 grams. This is what I do in Chem 1A for this. But you use it a lot in Chem 1B, unfortunately. I didn't even have to do the calculation, I was here. You can see that. Minus 3 point, okay, so how much energy is that? This is going to be in joules. All right, let's go to the next slide. It's on the next slide. Oh, it's not on the next slide. Did someone calculate it? Okay.
How do you get that?
Well, hopefully by multiplying that
The negative 12, sorry.
times 10 to the negative 12. Joules, or 10 to the negative 9 kilojoules probably. Or no, it would be the opposite, 10 to the negative 15. Well, anyway, that's that. Now, what is this energy? This energy is what we call the nuclear binding energy. Yeah, this is the energy holding the nucleus together. So small atoms have small nuclear binding energy. Big atoms have huge, enormous nuclear binding energies, right? But does that mean all small atoms are stable and all big atoms are unstable? No. What we have here is this. We need to normalize this. To compare nuclids, to compare nuclei. I'll just say nuclid. And so what we do is we get the nuclear binding energy per nucleon. Per nucleon. You know what a nucleon is? A nucleon is a proton or neutron. I'll just use these symbols, proton, neutron. And so what we can do is we can see this. A high nuclear binding energy per nucleon means it's a stable nucleus. And so the higher the nuclear binding energy per nucleon, the more stable the nucleus. Increasing nuclear binding energy, NBE, per nucleon means increasing stability. And so what we want is we want a high nuclear binding energy. And this is another thing you want to ask the theoretical physicists to do. Can they predict what the nuclear binding energy per nucleon is? Is it going to be the same for each nucleus? No. As some nuclei are unstable, some are exceptionally stable. And so we want to be able to predict that, but right now we don't. We just measure. Well, you don't measure, you just calculate it. You calculate it by determining the mass, the mass defect. By looking at the mass defect, you can get this, and then you see what has the highest nuclear binding energy per nucleon. It's mass number 60. What is mass number 60? Well, it has a mass of around 60. Nickel, copper.
I think
Well,
it's nickel, because that's the average of the different ones. Should
yeah.
be-
Well, anyway, it's in this area, iron, cobalt, nickel. Those are very strong nuclei. Chemically, obviously, they're reactive, right? But this is nuclear chem we're looking at. And so that has a very high nuclear binding energy. What has low nuclear binding energies? The extremely light elements like hydrogen, helium's way up there. Hydrogen has a low, some of the isotopes of hydrogen, and the lighter elements here. The lighter elements and the heavier elements. And so we talked about nuclear synthesis. The reason why nucleosynthesis works, that is why we can fuse together lighter elements, is because when we fuse together lighter elements, it forms heavier elements which are more stable. And so this is the idea behind fusion. Fusing lighter elements to form heavier elements that are more stable, have higher nuclear binding energy per nucleon. However, these transuranium ones are incredibly unstable because these are very short-lived, right? These don't live very long at all, but they can be formed for a fleeting moment of time. These ones are going the opposite direction. They're trying to take heavier ones and make even heavier ones, which are going to be even less stable, right? And so the way to stability is to take heavier ones and make lighter ones, so uranium, etc. That's fission. Fission is breaking apart the nuclei. And so these are energetically favored. Fusion for light and fission for heavy are what we expect to see. Well, here's the data. Now, do you see a pattern in the data? I asked you, let's ask the nuclear physicists. Well, the nuclear physicists have noticed the patterns, because if you take the observations and you look for patterns, and so what patterns are observed? Let's take a look at the patterns that are observed in nuclear stability. In nuclear stability, the first pattern is the shells. These shells are exceptionally stable. That is 2 protons, 2 neutrons. It's very stable. 8, 8, 20, 20, 28, 28. And so it's the magic numbers for nuclear stability. The magic numbers, these are the magic numbers. And the magic numbers, they think, correspond to shells in the nucleus, filling the shells, like filling orbital shells for electrons. And so that's called the shell theory, because the hypothesis is that the nucleus must form shells, and therefore that ends up giving us shell theory. This is the pattern that's seen. The other pattern that's seen is the even-odd. When Z is even, N is even, then the number of nuclides is very high, meaning that must be a good number, even. And so this must be very stable, even. A Z even and an N odd is less. A Z odd, N even is even less, and an odd is the worst combination based on the observations. And so what's the theory for this? Or hypothesis? You know, this is the pattern, so we gotta think. Well, right now, this is just pattern, you know, there's no at least this has some kind of hypothesis or kind of theory somebody proposed, you know. But this, what is it? And so this is what we want to know, right? So we'll come back to this and look at nuclear stability. We're almost done with this chapter, but just tomorrow I'm going to talk a little bit, and then tomorrow I'd like to review some stuff. So bring questions if you have it.